and we are starting a very important topic, namely parsing. Parsing is possibly one of the most successful topics in linguistics and natural language processing, in the sense that it has a very solid theory and excellent implementations based on that theory. Now, let us do one slide recap of the week of 19th August, that is last week, as we usually do. In the last week, we did discriminative part-of-speech tagging with beam search, where discriminative pause tagging made use of the features of the words. Pause tagging is a sequence labeling task. The sequence is sequence of words. At each position, we have a word, and we place a label at that position. We must understand that the label is not a function of only the word. Okay, if only the word was deciding the label, then no disambiguation would be required. We need the context around the word and also the properties of the word. For example, if a word is ending in tion, shun, it is with high probability a noun. Similarly, a word ending in ed is likely to be a past tense verb. All these features which are associated with a position. Okay, remember this distinction. The features associated with a position, not with the word. The word happens to be one of the features associated with that position. So those features are used to create the part-of-speech label at that position. And since multiple part-of-speech tags are possible, we do beam search for finding the best possible pause tag sequence. So it becomes a search problem. So the discriminating algorithm is a feature aggregator giving rise to a label, and the best possible label is like a search for the best possible path, and the path indicating the chain of part-of-speech labels, which is found out by beam search. And the beam search algorithm is a variation of what is called the A-star search, where the nodes which have to be expanded, the search nodes which have to be expanded, are limited by a beam width. Okay, so this point should be understood well. The difference between Viterbi and beam search should be clear in your mind. In beam search, we prune nodes which are candidates for expanding into their children. Whereas in Viterbi search, we prune partial paths, because we know that these paths with lower probability compared to other paths ending in the same state have no chance of winning in the end. So while we used Viterbi algorithm for searching in case of generative modeling based on hidden Markov model, we used beam search for discriminative part-of-speech tagging, where feature aggregation is done by the machine learning model. And in your assignment, you will be using a conditional random field for discriminative part-of-speech tagging. There are many features, but two features which have been suggested is the stem of the word and the affix of the word, like quickly as the stem as quick and ly as the suffix. So then in the last week, we covered a little bit of theory of conditional random field, keeping part-of-speech tagging in focus. So part-of-speech tagging is a sequence labeling task, and the conditional random field would give rise to a chain being found out based on the features around the position where the labeling is made. Now, conditional random field makes use of both look back and look ahead. Look ahead to the positions coming after the current position where the label has to be placed. And the look ahead is for a position which is ahead. And look back is usual in other part of speech algorithms also. So when you do look ahead, except for part of speech tagging, all the properties associated with positions ahead, which includes the words, their morphology, okay, as the signals for correct part of speech tag. Then we try to look at the pen tag set, which has become the de facto standard now for the tag set of any language. For English language, the UPenn tag set was used, and many other languages adapted this tag set for its purposes, including Indian languages. We took a look at the three evaluation matrix, precision, recall, and F-score. We understood why F-score is harmonic mean of precision and recall, because harmonic mean gives importance to lower of the two values. Arithmetic mean gives importance to higher of the two values, and that would be misleading. Okay, you can, when you improve the arithmetic mean, it is possible that the higher of the two values increases and nothing happens to the lower of the two values, but that's not what we want. We want both high precision and high recall. And since there is an inverse relationship between precision and recall, F-score is a trade-off between precision and recall. Then we understood by looking at rule-based part of speech tagging why a probabilistic part of speech tagging approach is inevitable, why data is inevitable. When we use rule-based disambiguation, we have to make use of a previous word to disambiguate the pause tag of the current word. By current word, I mean word at the current position. Now, if the word which is used for disambiguation itself is ambiguous with respect to its own part of speech, then of course there is a circularity, and that circularity has to be broken. We understood that 100% correct part of speech tagging is impossible. Whatever rule we give, rules can become very, very cumbersome if we want to reduce the error to a very, very small value. So we live with imperfection. We admit that probability of the probability of the part of speech level gives rise to a probabilistic scoring, which is good enough for us. Then we discussed your assignment on hidden Markov model, conditional random field. And we also have stressed that this time you have to benchmark your part of speech taggers performance against ChatGPT. There is a new thing this year because ChatGPT has arrived in the scene, and it does a very good job of part of speech tagging, parsing, and many other things. I've also remarked that your evaluation will be continuous, and in continuous evaluation, we would like to give a score using the following formula, that your score in any assignment would be equal to sum of the marks in various attempts divided by the number of attempts. So for example, for the part of speech tagging assignment, if in the first attempt you got a score of 90 and you will not attempt it anymore, then your score for pause tagging assignment, hidden Markov model based part of speech tagging assignment, will be 90. But if the first time you get 90 and the next time you get 95, then your score will be 92.5. Of course, there can be some kind of argument about why not take the best possible score. Here, my argument would be we would like to penalize many attempts that you're making. Not penalize maybe, but we would like to be fair for people who are doing the assignment in in one go, or maybe a small number of attempts. Also, we would like to appreciate your tenacity that you're trying to improve upon the assignment. And therefore, this formula, sum of marks in various attempts divided by total number of attempts. However, what is not acceptable is to do nothing initially and later you would come back and show your assignment and look upon that as one attempt. That is not acceptable. Okay, so we'll send you a cleaner note, more robust note with respect to your evaluation. But the point is that there is no deadline as such. You should be continuously working on your assignments and then bringing it up for evaluation. On 7th of August, you will have your assignment evaluation for hidden Markov model-based part-of-speech tagging, and 10 days later, CRF-based part-of-speech tagging. Okay. Now let us move to the discussion on parsing. Parsing produces a tree-like structure or a graph-like structure from the sentence. So we would like to first take a look at a very familiar example from arithmetic expressions. So arithmetic expressions are a sequence of numbers and operators. So for example, if you take a look at this expression 3 plus 4 into 5, then one possibility is that you keep 3 aside. Remember that it has to be added to something. That something is 4 into 5, which is 20. So 20 plus 3 is 23. So this is expressed by a tree-like structure where 3 is the left child of the plus operation. Plus is the central operation or the main operation in the sequence of numbers and operators. And plus is between 3 and the result of multiplying 4 and 5, which is also shown by this structure here. So you have plus at the root, left child is 3, right child is an operator, which is star. Star has 2 children, 4 and 5, saying that 4 and 5 need to be multiplied. Another way of performing this sum would be, okay, there's a little bit of error here. This should be same expression, 3 plus 4 into 5. So this would be 3 and 4 are added first, makes it 7. And then we multiply it by 5, which makes it 35. So clearly, this sequence 3 plus 4 into 5, without any precedence notion, evaluates to two different numbers, 23 or 35, depending on how you group them. So that is, the grouping is the central word in parsing. The tree that is shown, the two trees which are shown, are the two structures underlying this sequence 3 plus 4 into 5. And this is how we would like to create the parse trees of the sentences. So taking it to language, let us take the word unlockable. So unlockable has 3 morphemes in it: un, lock, and able. Unlockable has 2 meanings. It is un plus lockable, and lockable is lock plus able. So we first isolate the prefix and see the word lockable. So un plus lockable means something that cannot be locked. So this gate is unlockable. It is open and cannot be locked for some reason, let's say. So something that cannot be locked. The other possibility is we isolate able as the suffix and keep unlock intact, first of all, and then break unlock into unlock. So here the meaning is something that can be unlocked. This gate is unlockable. So the gate is shut with a lock and now it can be unlocked. So they kind of have exactly opposite meaning, the two structures. And the two structures are shown also here. Unlockable has left child as un, and then lockable as the right child. Lockable is broken up into lock and able, something that cannot be locked. And the other structure is unlockable at the root, and then unlock as the left child. Right child is able, and unlock, the internal structure is unlock, something that can be unlocked. Something that cannot be locked and something that can be unlocked. These are the two meanings. So just like the arithmetic expression evaluates to two different quantities, the word, the string of characters evaluates to two different meanings. We can say the meaning of a string of numbers and operators is its numerical value, the result of the operations. And the meaning of the string of characters is the meaning that it produces. Now, the fact that same sequence of characters produces two different meanings means that there are there is something which has two different values. And that something is what is called the deeper structure of the surface structure. The surface structure is the sequence of characters, and the deeper structure is this tree. And the fact that a linear sequence of characters or words have a deeper structure, that was understood long back. Okay, and that was the source of understanding that language has inherent ambiguity. Words, phrases, sentences, everything has ambiguity. So we should remember this very nice, cute linguistic insight that the start of parsing is in the fact that linear sequence of entities have multiple deeper structures, and these deeper structures evaluate to different meanings. So while we looked at the example of unlockable as a word, now let us look at a sentence, which is a famous sentence in linguistics as well as NLP. I saw a boy with a telescope. This sentence has two meanings. It is not clear who has the telescope. Is it me or is it the boy? So with a telescope, I saw the boy. It makes the meaning clear. I have the telescope and I saw the boy. And I saw a boy who has a telescope or who had a telescope. That also makes the meaning clear, where it is a qualifier for the boy. Now we look at the structure, the tree structure for the sentence. So here I introduce some symbols. S is the symbol for sentence. S consists of a noun phrase and verb phrase. So now we begin to note the meaning associated with a tree. The two children SP and VP, whose parent is S, means that this NP and VP are the constituents of the sentence of any sentence. Any sentence has two constituents, NP and VP. These are called constituents, the phrases within a sentence. Noun phrase is composed of a noun, and the noun in this case is I, instantiated to I. This is how the tree should be interpreted. S goes to NP, VP means NP and VP are constituents of S. NP goes to N means N composes the noun phrase here. Only one word, and that is I. VP, on the other hand, has more complex structure. It has two constituents, V and NP, that is verb and a noun phrase. And the verb and the noun phrase, the verb is instantiated to saw. The noun phrase has the internal structure. DET, that is a determiner. A noun, determiner becomes a, noun becomes boy. PP is a preposition phrase. PP's internal structure is a preposition and a noun phrase. The preposition is with. The noun phrase has an internal structure of determiner and N. The determiner is A, N is telescope. So this completes the deeper structure of the sentence. I saw a boy with a telescope. Okay, so this is the structure, and in this case, it must be clear from the proximity consideration that the boy has the telescope. How do we say that? Because you see the noun phrase has a noun phrase, a boy, and a preposition phrase with a telescope. The preposition phrase is sibling of the noun phrase a boy. This means the preposition phrase is modifying the noun phrase a boy. And the meaning of that is that the boy has the telescope. This is because of the structure of the tree. The structure of the tree is helping identify the meaning. So this is the syntax semantics relationship. Syntax helps uncovering the semantics. So because the preposition phrase is adjacent to a noun phrase, it is a modifier. So that is also the convention followed in phrases. If a phrase has two constituents and their siblings, then one of the constituents is what is called the head, the other constituent is the modifier. In this case, a boy is the head and the preposition phrase is the modifier. So we know from the structure of the tree that the boy has the telescope. Another constituency parse tree is possible. So S goes to NP, NP remains the same, I. The VP structure is now changed. We have the VP consisting of V, NP, a boy, and PP all at the same level with a telescope. So in this case, who modifies whom is the question. So the convention is that if it is a verb phrase, then the verb will be the head. Other things are modifiers. So in this case, NP and PP are the modifiers of the verb saw. So since PP is the modifier of saw, that means PP is associated with the verb saw and indirectly associated with I because I am the agent of seeing. So this structure is revealing the fact that I hold the telescope and not the boy. OK. So the question was that the question could be that a boy, the PP is the neighbor of sibling of NP also. How come PP is not modifying NP? The reason goes to the nature of the phrase here. The nature of the phrase is verb phrase. PP is a sibling of NP under what? Under a verb phrase. So that verb phrase must have its head as a verb, not as NP, not as PP. The head of a verb phrase is a verb. Everything else is a modifier. So NP is also a modifier. PP is also a modifier. NP is not a head. So PP cannot modify NP. It cannot be a modifier for NP because NP is not a head at all. V is the head. So this is how the structure is established, and we find that I hold the telescope is coming out from the structure here. So this is the utility of parsing. Parsing uncovers the deeper structure and it makes the meaning explicit because of the structural considerations. There is also an interesting aspect. That interesting aspect is that the proximity also decides who has the telescope. Now, if you take the word saw and take the path length up to the preposition phrase with a telescope, because our question is who holds the telescope? So this preposition phrase is closer to which word? So from saw, we have the path length to PP as 1, 2, and 3. 3 arcs are there. Whereas the path length to boy is 1, 2, 3, 4. 4 arcs are there. So PP is closer to saw than boy, and therefore it is a modifier for saw. What about the other case where the boy has a telescope? The PP is 3 arcs away from boy, but PP is 4 arcs away from saw. Therefore, PP must be associated with boy. So boy has the telescope. This is the proximity consideration. And it's a very useful tool for disambiguation. Now, what does part-of-speech tagging facilitate? Part-of-speech tagging is very useful because it is a feeder to subsequent processing. Subsequent processing means identifying chunks, which are small phrases, and identifying the parse tree, which is a deeper structure. Suppose we have this sentence: the brown fox sat in front of the fence. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 words in this sequence, in this sentence. The first processing that is done on the sequence of words is part-of-speech tagging. So we get here a DT, which is the part-of-speech tag of the, brown, which is the part-of-speech tag, JJ, which is the part-of-speech tag of brown. Now fox, and the part-of-speech tag is NN. Set, part-of-speech tag is VVD. In is a preposition, that's why capital IN. Front is a noun, NN. Of is IN, which is another preposition. The DT, determiner. Fence is a noun. So this is what is indicated. Then from the part-of-speech tag, we can obtain another sequence labeled output. This sequence level is called chunked sequence level. So the brown fox is called a noun chunk. It is like a noun phrase, but not exactly a phrase. It is a small chunk, and the small chunk of words. And another property of chunks is that it should not be recursive. A chunk cannot contain another chunk within itself, or another phrase within itself, but the phrases can contain other phrases within itself. For example, we saw that a preposition phrase can contain a noun phrase within itself. So the brown fox, and you can see here the part-of-speech tags DT, JJ, NN, which is usual. What are these new tags? B, NC, INC, and INC. Well, NC indicates a noun chunk. So, and B indicates a beginning. So we are saying that the is the beginning of a noun chunk. The other entities in the noun chunk being brown and fox. Brown is inside the noun chunk, that's why I. Fox is also inside the noun chunk, that is why again another I. And NC is the level for that chunk. So we are doing sequence labeling on the 3 words, the, brown, and fox. Okay, so BII. So this is called the BI notation, and is very important for chunking or small phrase extraction. And this often many times forms the heart of what is called information extraction, which is a vast area, sub area of natural language processing, and has immense practical utility. It serves the purpose of question answering, many times summarization, sentiment analysis, and so on. What are the other chunks here? Let us see. The fence. The is the beginning of the noun chunk. Fence is the begin. Fence continues the chunk. That's why INC. In front of is also a chunk. In is the beginning of a PC. PC means preposition chunk. Front continues the chunk, IPC. Of continues the chunk, IPC. So this is the way the chunks are formed. And forming of chunks is a high accuracy algorithm. This is also called shallow parsing. Both part-of-speech tagging and chunking are called shallow parsing. So shallow parsing produces short phrases, and it typically has high accuracy. If the part-of-speech tagging is accurate, chunks are also found out with high accuracy. Deeper parsing is different from shallow parsing in the sense that we find that a deep tree is created. In chunks, we again have linear sequence of levels. Here we have a deep tree. So the parse tree starts with the symbol S. S stands for the sentence, and it has 2 constituents, NP and BP. Remember that the constituents come as children of a node. NP has DT and NP, the brown fox. Brown fox itself is an NP with adjective and a noun phrase. Word phrase has these vint, vf, vvd, which are symbols, and these symbols indicate different structures of the phrases. PP we see has PG and NP. PG indicates a preposition group in front of, and the PP has DT and NN, the and fence. So it is because of correct part of speech tagging that correct chunks and correct parse trees are produced. Without very accurate part of speech, very accurate parse tree cannot be composed. Okay. Now parsing is always controlled by what is called grammar rules. And what we see in front of us now is a set of context-free grammar rules. So S goes to NP VP means a sentence is composed of NP and VP. The interpretation of the arrow is goes to or constitutes S or constituted of. S is constituted of NP VP. NP or a noun phrase can be formed in multiple ways. NP can be a determiner and another noun phrase, the brown fox. NP can be an adjective phrase and a noun phrase. Okay, a string of adjectives and a noun phrase. Bright blue eyes. Okay, vast blue sky. So that would be example of adjective phrase and noun phrase. Preposition phrase and noun phrase also can form a noun phrase. So the man with a mission. Man with a mission. Okay, man with a mission. Uh, uh, yes, so that would be following this structure. A noun phrase also can be a plural noun, N and S. Noun phrase can be a single noun. Now we see that many of the rules are recursive. That means the left-hand side is repeated in the right-hand side, thereby giving rise to possibility of infinitely long strings. So this was an important milestone in natural language processing, the advent of generative grammar. Generative grammar, it's a grammar. These rules are grammatical rules, and it is called generative because it can generate the strings of the language. So with these lexical items, am, is, shall, go, see, sat, when, fox, fence, brown, and so on. In front of is a preposition group, in lieu of is another preposition group. So using these lexical items, which are words and phrases, and the grammatical rules, we can compose long sentences. Okay, the brown fox sat in front of the fence. This grammar will be able to generate this sentence. The brown fox sat in front of the fence. So we are reminding ourselves that parsing is pretty high up in the NLP stack, which rests on how accurately morphology has been done, which supplies features to the layer of part of speech tagging, which supplies information to shallow parsing or chunking, creation of extraction of short phrases, and how it fits into parsing, creating the deeper structure, how this fits into semantics, which is words and disambiguation and semantic role leveling, and finally discourse and co-reference processing of large pieces of text. Now, semantics and the layer of semantics where words and disambiguation and semantic role leveling is done, it must have accurate parsing. And if there is any ambiguity at the semantic level, there will be multiple parse trees created. A good example of that is flying planes can be dangerous, where what is dangerous is not clear. Act of flying can be dangerous, or the planes which are flying can be dangerous. Now, if it is act of flying which is dangerous, then planes are the objects of flying, and the semantic role for planes is object. And if the planes themselves are dangerous, then flying planes are the subject, and flying is an attribute of planes. So it is coming as a qualifier for planes. Whereas if flying is dangerous, then plane is coming as an object for flying. So this kind of ambiguity can be seen at the level of semantic roles also. And this part of the diagram, which is emphasizing the three-dimensional view of NLP, namely problem axis, algorithm axis, and language axis, is saying that for parsing also, depending on the language, the approach, and the algorithm, the technique could be different. Okay. For example, if you're doing parsing for agglutinative languages like Dravidian languages, Hungarian, Turkish, Arabic, Manipuri, then we'll have to break long strings into small parts, their morphemes, and then think of linking them together through parsing. Okay, then we come to the point of shallow and deep parsing for different sentences. Here is an example. This sentence is Air India women pilots to fly over North Pole on world's longest air route from Bangalore to San Francisco. So Air India women pilot. Air India is a named entity. It's a proper noun. It's an organization. That's why B org and I org. B indicates beginning of the chunk. I indicates inside the chunk, which continues the chunk. Women pilot. One question that can be asked is that how come Air India women pilot is not a chunk? Okay. The reason is that a chunk should not contain another chunk within itself. Okay. So if you chunk Air India women pilot, you will have to have uh, three chunks, Air and India, and women will be one chunk, pilot will be another chunk. You can also combine women pilot, saying that women pilot, just like blue sky, form a noun chunk. But combining Air India with women pilot will not be possible. That will lead to construction of a phrase. Okay, phrases can contain other phrases within them, but chunks have to maintain a linear structure. Another chunk we see here is San Francisco. San is B, Francisco is I, and the label is GPE. GPE means geopolitical entity. San Francisco is a place, so it is chunked. The symbol O indicates these are outside of chunks. Okay. Now, why there is O here? So what is shown here is named entity labeling, and you have an assignment for named entity labeling using support vector machine. There you have it, two-way classification, name or no name. So Air India is a name, San Francisco is a name, Bangalore is a name. So that's why these have been given these BI labels, indicating that in this text there are these named entities. Fly is not a named entity or a proper noun. Women is not a proper noun. Pilot is not a proper noun. That's why O. This convention of labeling comes from what is called CONLL. Okay, Computational Natural Language Learning Corpora, which created the standard for this kind of BI notation. Let us examine the structure of Air India women pilot. Women pilot together form a composite entity. Women is modifier, pilot is the head. Air India is also a composite entity, but it is a proper noun and it is modifying the structure women pilot, the structural entity women pilot. So that is shown here in this diagram. Now, when we parse a sentence, we uncover its deeper structure. Here is a sentence which is metaphorical in nature. The detective listened with a wooden face. How can the face be wooden? Face is composed of bone, flesh, nerves, blood, and so on. How can it be wooden? It is used, the word wooden is used here in a metaphorical sense. Wooden here means expression less. On the face, there were no expressions or display of emotions. So we see that here there is a noun phrase under S. The detective is the noun phrase. And then there is a verb phrase, listened with a wooden face. So under the verb phrase, we have VBD, listened, which is a past tense. And then a preposition phrase, with a wooden face. A wooden face forms a noun phrase, which is why an NP is shown here. With is a preposition, that's why IN. So PP and NP together, sorry, a preposition and a noun phrase together is forming a preposition phrase. The preposition phrase is now a sibling of verb VBD, which is listen, and these two together form a verb phrase. Okay, so this is how we are creating the parse tree. Now this parse tree has the convention of the pen tag set. This is the parse tree, and the convention is coming from the tree bank corpus. And then you have the dependency parse tree also, where the and detective are linked together. This is called a determiner. Listened and detective is of listen and detective is again of a link structure, where n subject is linking listened and detective. Root is linking with listen. We're saying that listened is the main verb of the sentence. And the preposition phrase is starting with. So listened and with is linked by the predicate prep, means that listened is linked with. And determiner is linking face and a. Adjective modifier is there as wooden. Wooden is modifying the noun n. And with is taking face as the preposition object. So this kind of dependency structure is done by what is called the dependency tree creation. And this is indeed two ways of doing parsing. So we'll do both of these properly, and constituency parsing and dependency parsing. Both will be done properly. So the bracketed structure is still a sequence leveling problem. The bracket levels come between the positions while other levels come on positions. So this kind of parse tree also can be represented by means of what is called the bracketed structure. When we do probabilistic parsing, that is data-driven parsing, we'll see how the annotated data looks. Now, what is the need for parsing? Parsing actually facilitates many downstream important applications of in natural language processing. For example, let us take the case of sentiment analysis. In sentiment analysis, somebody expresses as an opinion about an entity, many times about some aspect of an entity at a particular time. So sentiment analysis is expressed mathematically, rigorously, by a 5-tuple representation. The first component of this 5-tuple representation is entity E. A is an aspect of the entity. S is the sentiment. H is the opinion holder. And T is a time when this opinion is expressed. Okay. So this 5-component tuple is a formal definition of sentiment analysis. Let me take an example. I loved the songs in the movie, though only the cast was liked by my brother. So here there are two persons holding an opinion or a sentiment about two aspects of an entity. The entity here is movie. And there are two aspects, songs and cast. I like the songs and my brother liked the cast. Most probably the implication is I did not like the cast and my brother was not very impressed with songs. Similarly, another example is I love the color of my Motorola phone back in 2000. Here the sentiment is positive. The entity E is the Motorola phone. Aspect A is the color. Opinion holder is H, which is I, and the time for the opinion is the year 2000. So this is how the entities are extracted from the sentence and they're linked by dependency parsing to capture who has what sentiment about what at which time. So since there are many entities participating in the sentence, it is important to isolate these things. And after isolation, we create what are called these opinion holder, sentiment, and aspect triples. I love song, brother like cast. This is extracted. These triples are obtained from the sentence. Before the break, we said that from the sentence, entities can be extracted and they have to be linked properly so that the sentiment analysis is done properly. Who has what opinion, at what time, about which entity, about which aspect of the entity. Those things are uncovered by correct parsing. Moving forward, two kinds of parse representations exist: constituency parsing and dependency parsing. In constituency parsing, we isolate the phrases and form bigger phrases, making sure that the correct constituents are identified. For example, the first constituent in any sentence is NP and the second constituent is VP. So NP is noun phrase, VP is verb phrase. Under NP, it has its own structure. Under VP, also we have the verb phrases own structure. On the other hand, the dependency parsing is totally controlled by the main verb of the sentence. First, identify the main verb and link other entities inside the sentence with the main. So there we see two kinds of entities, arguments and adjuncts. Arguments are essential entities which meet the requirement of the verb to form a sentence. Adjuncts are additional information. So for example, if I say I give, so then the sentence is not complete. Give what and to whom? So those things are called arguments. So I give a book to John. But adjuncts would be I gave a book to John in the library. In the library is not essential to complete the sentence. Okay, the syntactic requirement of the sentence is met only with the giver, what is given, and who is the beneficiary. The time and location of the giving activity is not needed for syntactic requirement. Both parses, dependency parses and constituency parses, help each other. If the phrases are identified correctly, then we know that siblings forms the head and modifier relation. In dependency parse trees, we link the head and the modifier. So correct identification of phrases help in creating dependencies. Similarly, since heads and modifiers are identified in the dependency tree, putting this head and modifier together create the correct phrase. Okay, correct phrase of the sentence. So dependency and constituency actually help each other in terms of head modifier forming a phrase. Dependency approach is suitable for free word order languages. Languages which can place nouns at different relative positions with respect to the main verb. So for example, in Hindi, Ram ne Sham ko dekha, Sham ko Ram ne dekha, both have the same meaning, even though Ram and Sham have interchanged their position. Who has seen whom? That information is encoded in the suffix ne and ko. It is because of ne and ko that we can take liberty with positioning of Ram and Sham. Of course, we have to move ne and ko along with the nouns. But in English sentence, Ram saw Sham or Sham saw Ram, where Ram and Sham have interchanged their position, the meaning also has changed. The agent of the seeing activity and what this agent has seen, they change depending on the position. So in English, the semantic role or who is doing what to whom, that information is encoded in the position of the nouns. Now, some important observations is that the pre-word order languages encode the special component of the meaning called semantic role in its affixes or postpositions. So ne and ko, for example, in Ram ne and Sham ko, encode that position. Or in affixes, for example, in mane. In case of mane, there is no postposition. That is, the suffix is not separate from the main word. In the non-free word order languages, like in English, we have to encode the semantic role information in the positions. Agent is normally to the left of the main verb in English. Chinese is an interesting case, which is loose with respect to both word position and affixes or prepositions. So this is why the Chinese processing would prove a difficult challenge for natural language processing, because they're both the position and affixing are loose in case of Chinese. In Chinese, which is an isolating language and its morphology is not very rich, we do not have lots of affixes or postpositions to encode the semantic role. Nor can we rely completely on positions, because positions can be taken liberty with. So in Chinese, context plays a very important role for disambiguation. Now, having said that, let us discuss some important algorithms for parsing. These are rule-based algorithms. They came in the early days of parsing, and that was replaced by data-driven parsing, that is called probabilistic parsing, which will be our next topic and an important and extremely interesting topic to discuss. The algorithmic mix of parsing in the early days of parsing saw the following situation. The problem statement is same, of course, in all different paradigms of parsing, different generations of parsing. The input is a grammar rule, is a set of grammar rules, and the input sentence. The output is a parse tree. The parse tree could be constituency or dependency. By now, the difference between constituency and dependency must be clear to you. In constituency, we isolate the phrases which come together. In dependency, we isolate the main verb and then link other entities with the main verb. Now, in case of top-down parsing, we start with the start S symbol, and we begin to look for the constituents which can be children of the S symbol. We look for the noun phrase, we look for the verb phrase. Now, under the noun phrase, we look for its constituents. Is there a determiner and noun? Is there a string of adjectives and noun? Bright blue sky, bright blue balls, for example. So this kind of structure is looked for in under NP. Under verb phrase, similarly, we look for the verb which forms the head of the verb phrase and other entities which form the verb phrase. So this is the top-down approach. You start from S and begin to develop the tree. In case of bottom-up approach, the workflow is opposite. The words are first resolved to their part of speech tags, and then the part of speech tags are combined by a constituency rule. For example, the noun phrase is composed of DT and NN. DT is the part of speech determiner and NN is the noun. And this process is repeated and with a typically recursive process where phrases are combined together to form bigger phrases. So we can form a noun phrases through the combination of an adjective phrase and another noun phrase. Okay, so bright blue balls. Bright and blue will form the JJP, that is the adjective phrase, and NP is balls. Okay. So now the main operation in parsing is to do a left to right scan of the input sentence. At every word, we decide if the word should create a new constituent or wait until more words get a look in to create a constituent. Okay. And on creation of a new constituent, examine if the new constituent can be merged with an adjacent one to form a bigger constituent. Let us illustrate this process. And it has a basic methodology called shift and reduce. So suppose we take the sentence, the boy plays. First, the input pointer, which is looking at the string of words or the front of the sentence, that pushes the into a stack. Then that leaves the two words boy and plays, the remaining part of the sentence, in the input tape. We call this entity which is holding the sentence as the input tape, and where the words go into and are resolved with symbols there. This is called a stack. So the has gone into the stack, boy plays is in the tape, and this is called a shift operation. Now the is resolved with a part of speech tag DT. The input pointer is still looking at the sentence itself. So boy and plays, they are these two words are in the input tape. Now we do a reduce operation. We convert, we replace the with DT, that is the part of speech. And then we are in a position to move the next word in the sentence. The boy goes into the stack. There is a reduce operation, then there is a shift operation. At this point, boy is reduced to NN, that is noun. And the DT and NN coming together forms a noun phrase. So two reduce operations are performed one after the other. Now a question that arises is that when plays is being seen, we could have shifted plays into the stack, or we can reduce DT and NN to NP, which has been done. Why did we prefer this reduce operation over shift operation? So that is a decision problem, and it is a continuously operating classification problem. Which amongst the two operations to choose? Should I shift or should I reduce? So typically a decision maker, a classifier, is operating at every point, deciding to shift or to reduce. And in a data-driven parsing paradigm, what happens is that this decision is made by a model which has been trained on data. All right, so let us illustrate the top-down parsing with this example. We have a very simple grammar. Sentence goes to noun phrase and verb phrase. Noun phrase can be composed as determiner and noun or a simple noun. Verb phrase can be composed as verb and adverb or as a simple verb. Now there are four kinds of sentences: declarative, interrogative, imperative, exclamatory, whose parsing we will discuss later. And the example sentence in front of us is people laugh. People laugh has these three indices. One, which is in the front of the sentence. Two is between people and laugh. Three is after laugh, the third position, which is the end of the sentence. And in the dictionary, we have people and laugh, which have two parts of speech, noun and verb. Laugh also has noun and verb as the part of speech. The top-down processing goes this way. We have on the stack the symbol S, which we are looking forward to expand. And one is the indication of the word scanner, the sentence scanner. It is looking at the beginning of the sentence. That's why one. So S is first expanded to NP and VP by making use of the grammar rule. S goes to NP and VP. And the input pointer remains the same. It remains at 1. NP is expanded to DT and N, determiner and noun, saying that I'm expecting to find a noun phrase in the form of a determiner and noun. And there is a backup state created because NP can also be a noun, as the grammar rule says. So backup state is n, VP, and 1. Now I do not find a determiner in the sentence. There is no the inside the sentence. It is just people laugh. So what I do is that I first consume people. People is consumed here, and then people will be satisfying the noun requirement. Now, since die is not found, we had to backtrack. Okay, we have to undo this, and we have to bring the backup state NVP, and the input pointer is still looking at 1. So at this point, I consume people because the noun symbol and the dictionary symbol of people are matching. So people is consumed. Now the input pointer moves by 1 position. It is looking at 2. So people has been processed. Now it is looking at laugh. So we have got the verb phrase now. The verb phrase is expanded as VADV, verb and adverb. The input pointer is looking at 2. The backup state is V. Now laugh is consumed. That brings adverb into the scene, but there is no adverb. The input is over, but the symbol on the stack is not yet over. So this means there is some mismatched expectation. That's why this parsing is called expectation-driven parsing or predictive parsing. So we undo the work and bring V from the backup state, also retract the pointer. So we have V and 2 as the state. Now laugh is consumed as a verb. The input is over. There is no symbol waiting to be resolved on the stack. So this finishes a successful parsing. And when we look at this whole scenario, this structure, we can constitute the parse tree from this. S goes to NP VP, NP goes to N, N goes to people, VP goes to V, V goes to laugh. That is the parse tree. So here the problem is that in top-down parsing there is useless expansion. So DTN, there is no determiner in the sentence. Why should we apply DTN? So there is useless expansion of rule. And also the other problem is that this top-down parsing can get into infinite loop if there is left recursion. If a symbol calls itself on the right-hand side, then it will keep on calling itself in the top-down processing. So these two problems exist in top-down parsing. So we go to bottom-up parsing where useless expansion of rules are not there, but useless bringing a part of speech can happen. So here we have the convention of a lower suffix s, and 1 and 2 indicates N1 2 indicates there is a noun between position 1 and 2. So we first start with S1 and question mark, which means I have to find the S symbol, but I still do not know the end of the sentence. It starts with 1, and we'll fill this gap as the processing proceeds. So now S is constituted of NP and VP, and there is this circle. It is called a handle, okay, or a dot. So the dot keeps moving over phrases, exposing new phrases whose work needs to be done. And to the left of the dot, we have a phrase whose work is over. Now let us take this our running example. People laugh. In bottom-up parsing, we are finding that between 1 and 2 there is people, and people from the dictionary tells me there is it can be a noun or a verb. So between 1 and 2 I have a noun or a verb. Now I have found a noun, therefore I have resolved a noun phrase because there is a grammar rule, NP goes to N. So there is a noun phrase between 1 and 2. It is also possible that between 1 and 2 there is a verb phrase. So these are the useless entities which are waiting to be resolved. So now the work of finding a noun phrase between 1 and 2 is done. It exposes the task of finding a verb phrase between 2 and the end of the sentence. So this is okay, satisfied because laugh is both a noun and verb. So by finding that laugh is a verb, the work of VP going to V is over. So then the dot symbol moves over VP and the whole parsing is complete. Here you can see DTN did not come, VADV did not come. So useless rules don't come, but useless parts of speech can come. useless left-hand sides can come. Okay, so these are the disadvantages and advantages of bottom-up parsing. So why not combine bottom-up and top-down together and have a parsing algorithm where the advantage and disadvantage of both are combined, and the disadvantages of both the top-down bottom-up parsing, where the top-down and bottom-up they alternate. Okay, they alternate and then create a very efficient parsing algorithm where useless rules do not come, useless parts of speech also don't come. But the disadvantage is that the top-down bottom-up parsing also suffers from the problem of infinite processing in case of left recursion. Let me end with a very well-known algorithm called CYK parsing. It's a very elegant algorithm. Let me illustrate this with an example. So suppose we have this sentence: the gunman sprayed the building with bullets. This is an ambiguity. Which bullet should go to building or to gunman? Of course, the semantics or the meaning of the sentence says that the gunman had the bullets. So here it is. The is between 0 and 1. The CYK parsing is controlled by a matrix where the rows are marked as 0 to the index before the end of the sentence, and columns are marked as 1 up to the end of the sentence, index up to the end of the sentence. So rows are 0, 1, 2, 6, and you can see there are 7 words in this sentence. So the index goes from 0, which is in the front of the sentence, to 7, which is the end of the sentence. So 0 to 6 are the rows, 1 to 7 are the columns. So first we find the between 0 and 1, and that is a determiner. So ADT comes here. Then between 1 and 2, we find gunman, which is a noun. So we have found a DT and an NN. From 0 to 1 DT, 1 to 2 NN. These two are adjacent. Now we can resolve them by an NP. So saying that between 0 and 2, you have a noun phrase, which is indeed true. The gunman is a phrase here. Then sprayed, which is a past tense verb, is found between 2 and 3, but we cannot find any bigger constituent, not from 0 to 3 or from 1 to 3, but only between 2 and 3. That is because we do not have any grammar rule which is saying that a phrase can end with VBD. So that's why these dashes are shown above VBD. Then between 3 and 4, we have the determiner and the building between 4 and 5. So a noun phrase is found between 3 and 5. This is correct. And sprayed the building becomes a verb phrase. This is between 2 and 5. Then there is nothing between 1 and 5, but the sentence gets completed between 0 and 5. The gunman sprayed the building is a correct sentence according to the grammar rules that we have been given. Then there is a preposition between 5 and 6, and a noun phrase between 6 and 7. Bullets is a noun phrase. Now the processing goes like a smooth trail, with the preposition phrase being found between 5 and 7. With bullets is a preposition phrase. Then between 3 and 7, we find a noun phrase, the building with bullets. And then between 2 and 7, we find a verb phrase, sprayed the building with bullets. Then between 1 and 7, nothing, because the has to be accommodated. 0 and 7, we find a sentence, the gunman sprayed the building with bullets. And if we look at the table, then we can uncover the parse tree this way, as is shown on the screen. So between 0 and 7, we have S, noun phrase between 0 and 2, verb phrase is between 2 and 7. And this verb phrase has 2 different parses, as shown in the 2 parse trees. So this we'll discuss in more detail later. And the parsing algorithms are either top-down or bottom-up. The CYK algorithm is actually a bottom-up parsing. So these are very elegant algorithms which are useful for processing sentences. They have also inspired lots of programming language parsing work.